While baking, air inside an oven undergoes a polytropic process with N equals 1.2. Okay, the air starts at P1, which is 150 kilopar, V1, which is 0.02 meter cube, and T1, which is 300 K. The final volume of the air is V2, which is 0.03 meter cube. Now, calculate the final pressure, which is P2. How much is done during the process? That's the work done. Then, how much heat was added or removed? So, we're told to calculate three things now: the final pressure, the amount of work that was done, and the heat that was added or removed. So we're given these other values. So let's write out our parameters that are given and let's know what we are to look for. Why? Okay, so the first thing we're given, they said N equals to 1.2. Then our P1 is 150 kilopar. Our V1 is 0.02 meter cube. Our T1 is 300 K. Then V2 0.02 meter cube. Is that correct? V1 is what? 0.02. Okay, V2 is 0.03. Sorry. Then we're given CV2 0.718 kilojoule per kilogram Kelvin. And we have our R, which is 0.287 kilojoule per kilogram Kelvin. And we have to look for our P2, then the Q, and the work done. So in our parameters, and these are the parameters given, and what we are asked to look for. We are asked to look for the final pressure, the heat, and the work done. Now, how do we know which formula to use? How do we know if it is this or this or this? Now, we're given our N to be 1.2, and this is the only formula that has raised to power N. So this is the formula that we are going to use. So we have to look for our P2. So we can get our P2 from PV raised to power N, that's 1 equals to P2 V2 raised to power N. So our P2 now would be P1 multiplied by V1 over V2 all raised to power N. Yes. So we can input our values. What's P1? P1 is 150. What's our V1? 0.02. What's our V2? 0.03. What's the N? 1.2. So calculating this is going to give us so this is going to give us 92.2 kilopar. So we've gotten our final volume. We're now to look for the work done. Which of the work done are we going to use? This is the formula we use to calculate this. Then that means we're going to use this work done. So which is W equals to P2 V2 minus P1 V1 divided by 1 minus N. So what's our P2? Is equal to this P2 92.2. What about V2? 0.03. P1 150. Then V1 0.02 minus 1 over 1.2. So this is going to give us 92.2 times 0.03. This is going to us 1.17 kilojoule. So they asked us to calculate our Q. So how can we calculate our Q? The only way we can calculate our Q is delta U equals to Q minus W. We already have our W, but we don't have delta U, but we can calculate it. So delta U equals to MC changing theta. Do we have our M? No. Do we have C? Yes. Do we have T2 and T1? We have T1, but we don't have T2. So that means we need to calculate our M. We need to calculate our T2. So if we want to calculate our M, we're going to use PV equals to MRT. And we're using all the values of the initial in the first stage. So this is 115. What's V1? 0.02. What's the M? That's what we are looking for. What's R? 0.287. And the first temperature, 300. So to get M, we have 150 and 0.02 divided by 0.287 times 8 times 300. So our M is 300. Yes. So our M is 0.035 kilogram. So now if we want to calculate our T, our second T, what do we do? Which of the variables do we have completely from our question? Since they didn't mention if it is constant temperature or constant pressure, but since we have V1 and V2 completely from our question, is there any formula that can relate the temperature that we are looking for to the volume? Let's check here. Okay, so we can use this. Yes, you can use that to get our T, our second T. So V1 equals to V2 over T2. So since we are looking for T2 to be T1 V2 divided by V1. What's T1? 300. What's V2? 0.03. And what's V1? 0.02. So what's our second temperature giving us? So we have 450 kilojoule. So since we have all of this, we should be able to calculate our delta U now. Our, what's it called? Yes, delta U. So our delta U now is MC change in theta. What's our M now? 0.035. What's our C? 0.718. Our change in temperature will be 415 minus 300. So what's our delta U going to give us? That is giving us 3.77 kilojoule. So from there now, can calculate our Q. We've gotten our delta U. We can now get our Q. Since we have delta U equals Q minus W. So our Q will now be delta U plus W. Our delta U is what? 3.77, and our W is 1.19, if I'm correct. That's plus 1.19. We have 4.96 kilojoule. Yes, and that is our answer. So let's move to the third question. In a soda stream machine, compressed CO2 undergoes isentropic. Okay, so they already know let us know that it undergoes an isentropic process. So from P1, let's write out our parameters. From P1, 800 kilopar, then T1, 300 Kelvin, then V1, 0.005 meter cube, to V2, 0.01 meter cube. Assume our gamma is 1.3. Calculate P2, T2, how much work, that's W, and how much heat is absorbed. Okay, so since we've gotten our parameters, now let's check where do we pick our formula from. Since they told us that it undergoes isentropic, then that means we are picking our formula from here. Now we're given one pressure, one temperature, one volume, sorry, two volumes, the ratio, and we have to look for P2 and T2. So that means the formula, they didn't mention if it is constant temperature or constant pressure. But how we are going to know the exact one to use now is we want to calculate P2, right? So to calculate P2, I need three unknowns. So I can calculate one unknown. I have one P1, so that's number one known. C1, that's just number one known under temperature. V1, number one known under volume. V2, number two known under volume. So I already have two knowns under volume, and I have one known under pressure. So I can use that to get my unknown. Now my pressure unknown. Now please, you should know, so all these formulas you need to know it off head, because you won't be allowed to write it out like this, but so that you can get familiar with it. That's why I just wrote it like that. So now, since you know that what you need is what you now want is the pressure and the volume. Since you have two knowns of volume and one known of pressure, now let's check under our isentropic process which of them has pressure and volume. So let's check pressure and volume. Pressure. Okay, so this is it, isothermal. So that means the formula we are going to use to calculate our P2 now is P1 V1 and that Beatrice. Sir. Yes sir. Báwo ni night sir? Yes sir. A dúpẹ́. Fájì ẹ̀jọ̀ ṣé mo lè pè yín padà later? Yes sir. So we can use the formula P1 V1 equals to P1 V1 gamma equals to P2 V2 gamma. So let's write it out. P1 V1 gamma equals to P2. That's to calculate our P2, right? So since it is P2 we are looking for, we are left with P1 and V1 over V2 gamma. Yes. So our P2 now is what's P1? 800. What's V1? 0.005, then 0.01, all raised to power. What's our gamma? 1.3. So let's calculate this to know what our P2 is. So this is 324.9, so 325 kilo per. So we've gotten our P2. Now we have to calculate T2 too. So let's check for known variables and unknown variables. We have two known variables of volume and one unknown variable of temperature. So let's check the one that has temperature and volume temperature. So this is it. So to calculate for our T2, we have T2 divided by T1 equals V1 over V2 gamma minus 1. So what's our T2 now? That's what we are looking for. So it will be T1 V1 over V2 gamma minus 1. So which is equals to T1 is what? 300. Then multiply by what's V1? 0.005. Then 0.01 raised power 1 point. What's gamma again? 1.3 minus 1. So our final answer should give us so we have 243.67 degree Kelvin. So that's our T2. So what else are we asked to look for? We asked to look for the work done during the expansion. Calculate the work done. The formula we are going to use is this, which says W equals P2 V2 minus P1. Sorry, P1 V1 1 minus this. So what's our P2? We got our P2 the other time. 325. What's the V2? 0.01. Then minus, what's our P1? 800 times, what's our V1? Sorry, V1 is 0.005. Then divided by 1 minus 1.3. So this is going to give us what? It's going to give us 2.5 kilo. Yeah. So that's that about the question. Okay, they now ask that how many heat is absorbed or ejected. Since it's an isentropic process, there is no heat added or absorbed or ejected. So let's move to our fourth question. Let air in the streamer initially at P1. Let's write down our values. P1 is 100 kilopar. V1 is 0.03 meter cube. And T1 is 298 Kelvin. Undergoes two processes. So for the first process, it's a constant pressure. which means that P2 is also 100 kilopar. That's what it means. So at constant pressure, heating until T2. So heated to T2. Then the second process is isothermal compression. So second process, that's constant temperature. So that means T3, I have to look for P1, but we're given already. P2, we are V1, we are given, C1, we are given. So to calculate our P2, are we given? Okay, since they said it's constant pressure, then our T, now what we are looking for is volume. To calculate constant pressure, what's the formula for ideal gas constant pressure? So we have V1 over T1 equals to V2 over T2. And so you can calculate our V2 like that, which will be V1 T2 divided by T1. This is going to give us, what's V1? 0.03. Then what's T2? 400. And what's T1? 298. And this is going to give us 0.04. So the next thing is we are going to calculate the work done for this. And the work done is P brackets V square minus V1, which is what's our P now? 0, 100 into brackets, what's V2? We've calculated V2 already, 0.04 minus 0.03. This should give us 10 kilojoule. Then we can now calculate our Q. What's the Q? MCP T2 minus T1. Do we have our M? No. But we can calculate it using P equals to MRT. What's P1? 100. Let's continue. P1 is 100 times what's V? 0.03. What equals to M times what's R?
So guys, sorry, there was a break in transmission, so I'll just continue using voice note. So we've gotten the work done for constant pressure. Now we are asked to look for the heat, and to calculate the heat for constant pressure, our formula is Q equals to MCP T2 minus T1, and we're not giving our M in the question, so we have to calculate our M. So that was how the M came about. And calculating our M, we have PV equals to nRT. Since we have all other formulas, like we have the pressure for the first process, we have the volume, we have the what's it called again, we have the R, and we have the T. So we can just calculate our M. So that will lead us to M equals to 100 times 0.03 divided by 0.287 times 298. Now the 100 is the pressure, the T, the 0.03 is our volume, and divided by the R times temperature. So we calculated our M to be 0.035 kilogram. Now you can now calculate our heat since we've gotten our mass. So we just input all the values that we have. That's the mass times the constant pressure, that's the specific constant pressure, then multiply by T2 minus T1, then we get our Q. So we have to calculate for our change in entropy. So for change in entropy, the formula is MCP in T2 over T1. So I've explained change in entropy, that's under second law of thermo. You can check out the video for that. So our change in entropy is mcp in T2 divided by T1, and we calculated that to give us 0.01 kilojoule per kilogram Kelvin. So that we inputted our mass, the constant specific heat capacity at constant pressure, then our temperature, and our the T2 divided by T1. So now from the question we were made to know that the first process, like that the system was at constant pressure first. So as it went in the process, it now moved to constant temperature. So that means that it's no longer, we are no longer following that process. We've moved into another process, which is the second temp, which is the constant temperature. So we have to calculate the final pressure. We are also have to calculate our work done, the heat, and the change in entropy for the second process. So to calculate our P3, so since the system now is at constant temperature, we'll check for the formula that has to do with constant temperature. And the formula that has to do with constant temperature, we want to calculate our P is, that should be P2 V2 divided by P3 V3. Now since it's now another process, it is P2 moving to P3. You know, the first one, it was like initial stage moving into another stage, but now to calculate for P3, it's our P2 moving from, is our system moving from P2 to P3. So that was why we had P2 V2 instead of P1 V1. So it is now P2 V2 equals to P3 V3, since it is 2 moving into 3. So we calculated our P3 to be P2 V2 divided by V3, which should be equals to 100 times 0.04 divided by 0.02 to give us our 200 kilopar. Now we can now calculate our work done. For constant temperature, our work done is MRT in V3 divided by V2. So we would input that, since we already have our mass, we have our reactive, and we will just put V3 over V2. So for constant temperature, we have to calculate our heat too. For constant temperature, our heat would be, I mentioned that our Q is equals to W for constant temperature. So is the answer we got for our W that is going to work as our Q for constant temperature. Then we will now calculate our delta S. So since we have constant temperature for change of entropy, normally it's meant to be MCP in T3 divided by T2, but since the temperatures are the same, so now to calculate our delta S, since it's constant temperature, is now going to be Q over T. I'm getting our Q and our T, so we got our delta S. So, and I hope you understand all of this. If you have any question, don't hesitate to ask a question in the comment section. And this is where we'll be ending the video for this section. See you guys next time. Bye. Don't forget to like, subscribe, comment, share to your departmental group. Until next time, see you guys later. Bye.